Modern decentralized networks aim for one clear baseline, moving data instantly across the globe without relying on central servers. Distributed hash tables, or DHTs, solve part of this equation. By mapping data across distributed nodes, DHT lookups allow individual file chunks to transfer at high speeds. But this creates a paradox. As packets fly between nodes, they collide and pile up at a narrow gateway, the payment consensus layer. Uploading a file meant paying piece by piece. Requiring a transaction for every data chunk creates unmanageable friction. To test a way out of this trap, the Autonomi 2.0 distributed testnet was deployed across 74 nodes, spanning 3 distinct hardware providers and 7 geographic locations. Reaching market viability requires replacing the legacy infrastructure with simultaneous structural overhauls in transaction batching, domain-separated encryption, and node trust vectors. Raw network speed serves no purpose if the underlying transaction layer fails under the weight of its own input and output demands. Consider a standard user action on the legacy network, like uploading a file divided into 100 individual chunks. The legacy architecture created heavy mathematical drag. Those 100 individual file chunks required 100 separate linear payment transactions to be verified by the network before the upload could complete. The structural solution is Merkle batch payments. 100 individual transaction squares merge upward through a hierarchical tree structure. By hashing data at each branch, all 100 chunks are mathematically proven and executed as a single consolidated transaction. The payment bottleneck is bypassed, restoring near-instant network I/O. Bypassing the bottleneck is only half the mandate. The payment layer also requires structural hardening against emerging computational threats. To secure these batch transactions, the network implements a specific cryptographic standard known as MLDSA65. MLDSA65 is a post-quantum digital signature algorithm designed to resist decryption by future quantum computers. This post-quantum cryptography is applied end-to-end across the entire payment layer, protecting the data continuously rather than at isolated checkpoints. This exact batching architecture has already passed continuous integration testing, running green on a live 35-node testnet. By mathematically decoupling the volume of data chunks from the volume of ledger transactions, the network's I/O capacity is no longer chained to the speed of its consensus layer. Securing the payment transport is critical, but the security of the individual data payload requires its own architectural focus. The release of the v35.0 self-encryption upgrade addresses this by deprecating and stripping out all legacy encryption formats. A dual-layer protocol wraps a data block with a BLAKE3 hash, sealed by a thick ChaCha20-Poly1305 outer boundary. The block multiplies, and unique algorithmic keys attach to each. A barrier isolates the keys, ensuring domain separation so they cannot be maliciously exploited elsewhere. Much like the upgrades to the payment layer, this data layer overhaul directly aligns with the network's mandate for quantum-safe architecture. User data is mathematically isolated and structurally fortified before it ever leaves the machine to touch a decentralized node. With the data heavily encrypted, the engineering focus shifts to the physical and mathematical logic of where it is stored. The core vulnerability of the 1.0 architecture was routing data based on physical proximity. This diagram shows a central target node with hostile nodes aggressively clustering around it. Bad actors could exploit this bias to surround and capture targeted data simply by spinning up nodes nearby. The Autonomi 2.0 defense mechanism is a multidimensional node selection vector that redefines network topology. The first new parameter evaluates behavior. Nodes must now maintain a mathematically quantifiable trust score to be eligible to receive data. The second parameter enforces geographic distribution. Data payloads are spread across disparate physical locations to prevent localized capture. The third parameter mandates provider diversity, distributing data across different hardware providers' infrastructure to prevent vendor-specific vulnerabilities. The active testnet is currently stress testing this model, verifying data dispersion across 7 distinct geographic locations. By combining trust, geography, and provider metrics into a single selection vector, the network structurally neutralizes the proximity attacks that limited early iterations. Autonomi 2.0 enforces network trust through a multivariable equation, moving past the blind assumptions based on distance. Translating theoretical network design into a live system introduces the operational realities of bootstrapping. Managing a 102-node testnet operating concurrently across Linux, Windows, and macOS environments carries significant engineering complexity. To manage this complexity, the engineering team uses network-wide auto upgrades. This technical schematic shows a single central server node actively pushing a unified code package out to an array of different operating system icons. The immediate engineering benefit is the ability to achieve rapid iteration and deploy patches across a fragmented hardware landscape. But this creates a direct architectural contradiction. Auto upgrades are inherently centralized because all participating nodes must trust a single source pushing the code. Centralization serves as a pragmatic, temporary necessity required to accelerate iteration and push the network toward an early launch. The firm engineering principle stands: a permanently auto-upgrading network is not truly decentralized. Once network stability is reached, the auto-upgrade mechanism will be removed. Network engineering treats pure decentralization as the mathematically stable destination of the project. Beyond the hidden back-end architecture, everyday users interact directly with a human-facing access point to navigate the network. That gateway is called Indelible. Alongside the Autonomi desktop app, this actively tested user interface serves as the primary entry point to the upgraded network. Indelible surfaces critical management capabilities directly to the user, integrating wallets, API tokens, node management, and data quotas into a single interface. This interface is backed by a vital architectural cleanup: the strict enforcement of default logging off in production environments. Disabling logging at the core eliminates metadata leakage, cementing the privacy of the human interface. The final engineering sprints are now focused on refining replication systems for reliable downloads and finalizing the precise mechanics of the trust model. With these systems verified, the target timeline is set, bringing the fully upgraded Autonomi 2.0 network live in early April. With post-quantum batching, domain-separated encryption, and multi-vector routing locked in, the architecture is finally capable of bearing the weight of true decentralization.